Let me just find the slide that we got to. I've updated the slides online. They are approximately what I'm using. So if I recall correctly, we'd gone through all of the introduction stuff and we got as far as the Sudokus. So now we're going to watch yesterday on fast forward. Be fun for everyone. I love fast forwarding through every stage of the builds. Right, SMT lib Sudokus. Yeah, okay, so just so that we're starting where we were yesterday, we had built a formula for solving Sudokus. We'd done that by representing our sort of Sudoku grid as an uninterpreted function, and we created this set of assertions that define the rules of, that assert the rules of a Sudoku, and we'd solved it, and we discovered that we can solve Sudokus. Yeah, so we now no longer need to spend our valuable weekends looking at newspaper Sudokus and trying to solve them by hand, because we can do it automatically. What I'm going to tell you now is some other ways we could have done this. And then we're going to move on to the 3 different examples that I have of applications of SMT. And we might not have time for all 3, so we might have a bit of a vote on which one, on what order we want to do them in. But can we solve the Sudokus better, or at least differently? So suppose I'm working my way through all of the Sudokus in the weekend papers. A lot of my Sudoku constraints are the same, particularly the ones that tell you how the Sudoku works. So one thing I might care about now is incremental solving and using push and pop. So I'm giving you this because it's useful, not because it's particularly academically insightful. But if you're solving multiple problems that are the same, what you can do is you can put a push before some of your assertions, and then your pop will remove everything back to the last push, which means that all of the work your solver has done to get to the point before the push, it doesn't need to redo that. So if so in the examples, I should have an example 6 with push pop. Something about using a terminal in front of people that immediately makes you not be able to type. Yeah, so what I've done is I've put all of the grid constraints, all of these constraints that tell you the rules of Sudoku, I put them before a push. And then what I can do is I can put the constraints that tell you what Sudoku we're solving. Then I can check that Sudoku, get the model, and then pop all of that off and then do another Sudoku. That should give us 2 solutions. Handy if you're solving a lot of problems at the same, which if you're applying this to model checking, you probably will be. Yeah.
Is there like an interactive session? Use this format to give back. If I get the model back, I will use that because that's the model display from the next spot.
Yeah, is there an interactive session you can use this for? Yes, absolutely. So you can run most of these solvers in interactive mode. CBC5 is an SMT solver. If you open that, it immediately opens it in interactive mode, and then you would just have to type your commands in, and you can stop and do something and then go back to it. Don't want to be in CBC5 right now, though. There is indeed a Python API, which I am not going to show you because they're specific to different solvers. So you. What would you like to do instead?
You might name some submodel and then use it. That's what we did in program.
Okay, there isn't a higher level interface that you are looking for. But it would, I suppose that if you wanted to have like modules that you can push and pop on, then you could So one of the things you could do is you could define that set of assertions as a function, and you could add that function before all of the pushing and popping, and then you could say assert that function, and then you could, so you can create like functions that represent more than one assertion in that way. Oh, also, this example is in the examples as well. You get errors if you try and assert things that don't exist, obviously. The next thing I want to tell you about is bit vectors, which do not behave like you expect if you're expecting them to be exactly like C. So one of the things they do is they divide by zero. Divide by zero is defined. So this comes from the thing where we said that SMT functions are defined across everything. So they're defined, like divide by zero will give you the maximum value you can fit in your bit vector. We don't have undefined things. We don't have exceptions. We don't allow that. If you look in the examples on the GitHub, I have added an SMT file that does the arrays with bit vectors. It's not any faster and it's less readable, but you will sometimes find that bit vectors give you advantages if you need to do bitwise arithmetic. And this also means that we can represent programming languages quite neatly, because we can simply say, oh, okay, a car is the same as a bit vector of width 8. This example is also in the GitHub as an SMT example, so you can run it if you would like. Another thing I haven't talked about, which I'm not really going to talk about in much detail, is quantifiers. So you can write quantifiers. SMT solvers by default support first order quantification. So you can quantify over variables. You can't quantify over functions in first order quantification. This can make things more compact. So if we did the array version, this means that we can write like the constraints for everything must be between 1 and 9. We can write that in a really compact way for the entire grid. The disadvantage is by introducing quantifiers, you're potentially making the problem harder to solve, because the SMT solver has to instantiate your quantifiers somehow. So it has. I'm not going to talk about quantifier solving techniques because we simply don't have time. But if you were to look at, say, e-matching and different quantifier instantiation techniques, it makes this a lot more involved. So quantifiers are useful if you're reasoning about arrays, but just be aware that sometimes you end up with very difficult problems. Also, it's quite easy to accidentally write things that are trivially false. So let's say I have 2 variables. I've got an array and I want to say that all elements of the array are unique. I might say, okay, so I'm going to create 2. I'm going to do this in math notation. So I might want to write for all ij, and then you tend to see a lot of beginners write things like this. And what you intended to write is you intended to say that for all elements of the array, they're not equal to other elements of the array. What does this evaluate to?
Unless there isn't.
Yeah, this evaluates to false because when I and j are the same, they obviously have to be equal. You can't have an empty array in SMT because your arrays have to be the size of the index sort. So if this is an integer, then your array is infinite. If it's
you can write implies I is different.
So what I would probably do is for all ij, I not equal to j implies.
That's the same.
Yeah. Wait, what are you suggesting?
Because if you put it the other way around, what they're essentially saying is that it's an injective function. In other words, if AI is equal to AJ, then I is equal to J means it's injective, which is exactly what you're writing.
No, okay, so what you're saying is if I'm the person that lost the border of it yesterday. So you're saying you want for all ij,
AI equals AJ.
AI equals AJ implies I equal to J. But
Because that's what a mathematician would.
I don't, but the property I want to know is I want to know that all elements of the array are unique. I think if I have an array that is what all the elements are the same, I think this is true, right?
No.
All the AI, all these inequalities are true, but all also the ones that are, right?
Yeah, so A0 is equal to 1, but 0 is not equal to 1.
Which is not what I want to say, right? I want to say that all of the elements of the array are different. So I want to say if the indices are different, I want to say if the indices are different, then the values are definitely different.
Oh, but that's exactly what this is.
That's what it is saying.
Because then if you pick I to be 0 and 2 to be and J to be 1, then you get a AI equals AJ, but then it should imply I equals J, but it doesn't, because 0 is not equal to 1. And then there's your comment.
You having the whiteboard effect.
You're
Step
right.
away from the whiteboard, you'll see it.
You're right. Okay, there's a very good example of why I often write things that assert to be false. Oh, you can define functions. This example is also in the GitHub. I'm not going to go through it. You can define functions. That is useful because then you don't have to write the same things all the time. So this was where we intended to finish yesterday. I was going to tell you there are other ways to build SMT files. You can use Python APIs. I put a link to a tutorial for the Z3 one. As far as I know, I think there is one for CVC5, but I think the Z3 one is the most mature one. And you can also use other tools to build SMT files if you don't like writing Lisp directly, which most people don't.
Like runtime or formula. I mean, I know you can kind of approximate it yourself, but like this.
Is there any?
Give you something like that, or
Is there any way of getting approximate runtime for formula? Not really. So we did a bit of work where we tried to predict what the best SMT solver was for a problem. And so given a set of SMT solvers, we try to predict which one is likely to be the best, and then you run them in that order. And as part of running them in that order, we also try to predict runtime. But to predict runtime, we essentially said runtime tends to be like, it tends to follow something like that. Like most queries are solved really quickly, and then like, there are the number of queries that are solved in a long time. So it's basically an exponential drop off. And then we also looked at using feature vectors extracted from the queries and using a kind of k nearest neighbor to predict the runtime. You can get a guess, but you can't really get better than that. And the features that tend to give you the biggest prediction are the sort of ones you expect to be the ones you expect. So it's things like, is the query massive?
you set like a cutoff determination, how many iterations or how many?
I don't know if the solvers let you cut off at the number of iterations, but you can obviously always set a time cutoff. But yeah. Okay, so these are the three things that in the next, what have I got? I've got about 70 minutes. We can try to cover. I would sort of roughly like an order of preference, but because I think we're going to do two of them, I want you to vote on what you are least interested in. So if you don't care about synthesis, can you stick your hand up? So your options, let me tell you what they are first. So we have SMT for synthesis. So we're going to use SMT to synthesize short expressions. And I'm going to show you how you can use that to come up with loop invariants. I have Euclid 5, which is a tool that lets you build models and then generate SMT queries for different verification procedures. So you can say, here is my transition system, give me, like, do bounded model checking, do K induction. And then you can also say, here is my transition system, and this is a hole, I don't know what goes in here. Can you synthesize something for that hole so that I pass these properties for bounded model checking or K induction? And I was also going to talk about using SMT to verify how permissive access protocols are, which is on S3 buckets at Amazon. So this is, they deploy, like if you use an S3 bucket, you've seen a little icon in the top right-hand corner of your list of S3 buckets, which says, is this bucket publicly available? And they use an SMT solver to tell you whether that's true. So if you care least about synthesis, can you stick your hand up? If you care least about Euclid 5, can you stick your hand up? If you care least about Zelkova, stick your hand up. What? What?
This book, you have to learn to murder your darlings, or let them be murdered by the
That was the most fun one. I've got a whole list of like the worst cases where people accidentally made their S3 buckets public. You know, it's like there's some US defense ones where like they released a whole bunch of sensitive military information. Okay, fine. In that case, we'll just do it in the order the slides are in, and we probably won't get to Zelkova, but we might. Fine. So let's talk about synthesis. So if I wanted to verify that this program on the left never violates this assertion, I'm not going to be able to do this with CBMC because, so if I don't know how far this unwinds. This has, so I'm using the star to indicate like a non-deterministic stop point. Assume that, like, I don't know, the user can put a key in or something that stops it. But whenever this stops, I want to assert that A is less than or equal to B. So I can't do this with bounded model checking. I can do this with induction, in theory. So if I can't, like the way you get unbounded proof in general, in software verification, is you try to do a proof by induction. So what you want to look for is, you want to say, okay, if my property holds initially, so you want to say, so I'm using init to mean the initial conditions. So when I say init, I'm assuming this is A is equal to 0 and B is equal to 1. So I say if my initial conditions hold, that implies my property holds. And then you want to say, okay, so let's assume that my property holds at some point when I'm entering the loop. And let's assume that I apply the transition relation. Then I want to know that the property still holds. I am using the prime to mean this is the next step. So when it says A prime, like that's the next, on the next step, A is that value. And then if I know that holds, I then like that's fine. Then my property is inductive and we proved it. Yes, what have I messed up?
Nothing. I just wanted to know what X,
Okay, so I have used X to be like broadly, this is the group of variables. I didn't actually notice I'd done that. In the classic notation for this, you'll always see this as X. X here is A and B. That was poor slide making. Yeah. So if that holds, if that's true, then we're absolutely fine. But I don't think that is true in this case, because so my property is A less or equal to B. And so I know that init implies the property, clearly true, but I don't think that A less than or equal to B and the transition relation implies that A prime is going to be less than or equal to B prime.
Are you assuming that they're non-negative?
No.
Maybe you need other functions than point.
Yeah. Okay, so as correctly pointed out, so to make this inductive, I need to assume that they are not. I need to assume they can't be negative. So that's the typical way if you want to do a proof by induction, what you tend to do is you write this out and then you go, oh, this didn't actually work because my property isn't inductive. And then you sit down and you try and figure out how to strengthen your property to make it inductive. So we can strengthen our property by adding that these are greater than or equal to 0. But this was easy for this case, but it's not necessarily easy. You can have massive models and really complicated sets of properties. Question?
So, taking through the process of the like, so you can prove by induction.
Yeah, so your proof by induction, you have the base case, which is that the initial conditions must imply that the property holds. And then what you want to get is you want to get your step case, and your step case should be, I assume that the property holds, and then I do the step, so I apply the transition relation, and that should mean that the property still holds afterwards. And this is only so the problem with this example is that this doesn't hold because this isn't an inductive property, but we can make it inductive by strengthening it. Yes. Sorry?
The determination, how do you stop?
How does the loop stop?
I don't know, how does the proof stop?
Well, once this actually, maybe I can show the.
I'm just thinking some version end up tending towards the base case. That's a great order tends towards the base case.
Let me give you the explanation of this on state space. So what we're effectively trying to do is we're trying to say that so assume this is A and B, I don't know, on some kind of two-dimensional space. These are my initial conditions. What we want to find is we want to find a space in the state space that we cannot leave and that is outside of the bad states, so that is contained within the property. And so, and what this says I cannot leave that space. So this says I'm inside the orange loop. If I apply the transition relation, still inside the orange loop, and then you know that you are safe forever, because for all possible, so this is like a non-deterministic start state, but where the property definitely holds.
So this is for safety, you can't use this for reachability.
I mean, I guess safety is the jewel of reachability, but yes, this is for safety. So all you can say here is I do not reach bad states.
Yeah, if you want to show that you reach a good state.
Yeah, then
That
you cannot use safety invariance to show that you reach a good state. Yeah.
What do you guys mean when you say reachability?
like you end in a good state, so or well, not necessarily well, I generally think there's something starting and stopping in the state that you want it to be.
Yes.
So what's the user experience mean? Is it going to see unknown? Is it going to see, I don't quite see why the invariant holds for the loop?
What the user is going to see is a counterexample, which will be a state where the property holds, where when you apply the transition relation, the property does not hold afterwards. And that state is not necessarily going to be reachable.
Right. So it's going to be like, oh, if A is negative and B is probably something.
Yes, exactly. Yes. Yeah. So what we want to do is we want to come up with this strengthening by ourselves. We want to come up with this strengthening automatically rather than making our user do it. So what we want to do is we want to find this invariant such that this formula holds. Yeah.
like if you wanted to prove that you've got to the right state, could you just add another condition and say, and not trans, and you're in the state that you care about?
So if you wanted to assert some property, you could, if you had a loop that had a loop condition and you wanted to assert that some property held after the loop condition, you could do something where you say that at the end, the invariant, you can't read if I write it down there, can you? You can do something where you say at the end, the invariant and not the loop condition implies that the property holds, or yeah.
Is that the same thing and not trans?
No, because your transition relation and not trans just would set, so trans gives you a predicate, which is true if you're taking a valid transition in the system. Not trans would give you a predicate, would give you a predicate that's true if you take any invalid transitions in the system. So in our example, if I went from A is 0 to A is 1,000, that would satisfy not trans. Okay. This is second order logic. Coming up with that invariant is second order logic. What I want to do is I want to find exist P such that for all X, some logical specification holds. In this case, it was, does there exist an invariant such that for all A and B, that set of conditions about the invariant holds. And that set of conditions was in it implies the invariant and trans implies invariant, and invariant implies the property. This is classic second order. There exists an entire sort of community of solver makers that solve these problems. And this is called SIGUS, which is syntax guided synthesis. And there is an input format, which is similar to SMT-lib, which is called SIGUSIF. I'm going to solve this for you, and then I'm going to tell you how they solve it, because essentially they solve it by multiple SMT solvers playing with each other. Is this problem decidable? In general, no, absolutely not. Absolutely not. There are cases where this problem can be decidable. Let me solve it and then we'll talk about it.
Take each X to be a program, each of the defaults.
Okay, so can you read that? Is that big enough? Big enough? Okay. So this looks a lot like SMT-lib. This is SIGUS. There is some slight syntactic difference. Declare var means declare one of these universally quantified variables. And synth means synthesize this function for me, please. And constraint means this is part of that sigma. This is part of the specification. So what this is saying is for all A, B, and A prime and B prime, the conjunction of these constraints must hold. You can't see everything though because I got word wrap turned off. I don't know, but you're not. Yeah, I don't know. They don't allow apostrophe in it, so we've got an exclamation mark. There you are. That's the answer. It's given us the full property. It's told us that we need to make sure that A is greater than or equal to 0. If I can remember how to run it with debug, we can see what it did to solve it as well. Oh, there we are. Okay, so what it did to solve it effectively was it enumerated through the search space until it found something that worked. That's quite that makes it sound a lot simpler than it is. Yes, question.
Following on from Sam's question about
abstraction and spatial predicate.
Yeah.
You would like to get that. You were human. Would be the invariant I wrote plus some stuff. This
Oh,
just flattens it all out as so the invariant, the transinvariant is essentially replayed here, and then there's another clause. Is it capable of constantly following that back in so you can see what you originally wrote plus the extras?
I could have written the specification so that I asked it to strengthen what I'd originally written, whereas I asked it to come up with an invariant by itself. It is doing some tricks. So for invariant synthesis, it usually does some tricks where it takes the property fairly immediately and tries the property fairly immediately anyway, and then tries to strengthen it. One of the things about syntax guided synthesis solvers is if you don't give them a grammar to work through, so you can give a grammar for the solution. If you don't give them a grammar, they tend to come up with things that are quite esoteric and weird. That's just a feature. You often get things where, I mean, maybe it's just me that doesn't find lists very intuitive, but you often get things where it takes a while to figure out what the solution actually is. And if you had a human come up with it, they would have written something much more idiomatic. It's a feature of formal reasoning.
We use CVC5 for sensory design.
Okay, so I use CVC5 because CVC5 is both an SMT solver and a SIGUS solver. Z3 is just an SMT solver. There are other SIGUS solvers available, but I would always say use CVC5. It's more reliable. Okay, is this decidable? Oh, yeah, question.
What stops the solver from coming up with like a stronger invariant than it? Like if it just tacked on some other clearly true clause, like, and also like x is also greater than 5, right? This is going to be true, and sorry, a is greater than 5. Like what keeps that invariant minimal?
Nothing.
Okay, so it might actually be unreadable. So.
It can come up, yeah. I mean, what stops it tacking on stuff on the end is that it tends to enumerate through stuff starting shortest first. But there is nothing in my specification that stops it from coming up with something that is stronger than I need.
I just want to point out that it needs to follow from the initial condition.
Yes, yeah, it does need to follow from the initial condition.
Oh,
Yeah.
A.
Yeah, like you could tag all sorts of stuff on the end that is equivalent to true. Like it doesn't, yeah, this is the thing with computers. They always do exactly what you tell them to, and it's never what you actually wanted them to do. And SIGUS is a perfect example of that. Like you come up with what you think is the perfect synthesis specification, and it comes up with the most stupid answer you've ever seen. Like a classic one is you think, oh, I've written this specification, come up with this invariant, and it comes up with true or false because you've written the spec wrong. Yeah. So we are saying, does there exist a program P such that for all inputs to P, which I called X, sigma P X, or well, X is you don't have free variables in here. So X is all the variables that are nullary. And then P is the function that you want to synthesize, or possibly the set of functions. Decidable. It's not decidable in general. If P takes a finite set of inputs with a finite set of values, for instance, if P takes bit vectors, this becomes, and you have not provided a syntactic template, then you should be able to find a solution, because the worst case scenario, you just come up with a big switch case that says if the input is this, return this. If you have provided a syntactic template and your syntactic template is finite, so a syntactic template is a grammar. If you've provided a grammar that only has a finite number of programs in it, it's decidable. In general, assume it's not decidable. There are some other weird cases in the middle where it is decidable. But how do we solve it? Okay. I'm pronouncing this SIGUS This is counterexample guided inductive synthesis, which I have not written on any of the slides. Counterexample guided inductive synthesis. Almost all solvers that do any kind of program synthesis that is guaranteed correct are doing CGIS. Anything that synthesizes code is doing some variant on CGIS, unless it's not necessarily synthesizing correct code. If you've got like Copilot, it's not doing CGIS, but it's also telling you things that are probably wrong. So in essence, CGIS has a synthesizer, which is a guesser, and a verifier, which is probably an SMT solver. So your synthesizer makes guesses about appropriate programs. Your verifier says yes or no, that is correct or it's not correct. If it's not correct, it should give you some kind of feedback so the synthesizer can make a better guess. So, oh, there's some fun scribbles on this that weren't there before. Okay, so if we start off, let's assume that our synthesizer has given us a candidate. Let's not think about how it does that first. So it's given us P star, which is a candidate. We give that to the verifier. And what we want to know from the verifier is we want to know, is there an input that makes the spec false for P star for our candidate? So we substitute P star into our spec sigma, and we look for an input that makes it false. And that input is called a counterexample if we find it. And that is a straightforward SMT solving problem. We can give that to an SMT solver. If we can't find one, then our program is correct for the whole specification. Like if we can't find one, then we're done. If we can find one, we've got a counterexample. And we give our counterexample back to our synthesizer. Our synthesizer keeps a list of all the counterexamples it's found before, and our synthesizer tries to find a P star that works for all of the counterexamples it's seen before. What this is doing is this is breaking down a second order formula that we couldn't solve into some slightly simpler formula that we can solve. So if this list xi of counterexamples we've seen, this is finite and hopefully small, which means that we can turn this for all into a conjunction, which means this is a formula that we can actually solve. So, wow, this slide is a mess. I'm sorry about that. Yeah, if the synthesizer is unsat, then we just give up. If the synthesizer is sat, we continue the iteration until eventually we finish. So your verifier is basically almost all of the time, it's going to be an SMT solver that gives you counterexamples. Sometimes you might have a tester that runs it on input-output examples, but basically all the time it's going to be an SMT solver. What goes in the synthesis box? So there are options for the synthesis box. We could, yes.
So in the unsat case, something that might happen is we'll say unsat, but then we can inspect all the examples. They actually, this example you cannot use outside the spec, and just like the spec to exclude. Is something that will happen in practice?
In the unsat case, so if the synthesizer says unsat, could you inspect the counterexamples and check if the spec, and then have a human decide if the spec was overly restrictive?
Yeah, so -5 give you 3, and that's that doesn't say, oh yeah, there's no negative input in this spec, so I should strengthen this spec. Really?
I see what you mean. I see that could be useful. I don't know of a solver that actually outputs that for you, though.
Thanks.
Yeah, I see that would be useful, but you won't normally see that from a solver.
Why do you have those, and why wouldn't you use the parameterizer there? Because the input going into the program.
So I've said that sigma is a specification which takes P and X in. This is just notation, which I possibly have slightly abused. So what this is saying is I have some spec where I have like I've used P and I've used X and then I'm substituting them in. But I could have made better notation for that.
I'm free to pick sigma.
So
Am I free to pick sigma?
yes, sigma is your spec.
So if I can write, so if I write, let's say, an interpreter, and then I'm searching for a program.
You are not free to pick sigma outside of like it has. What I am telling you about now, sigma has to be part of. You have to write it in SMT. So you have to be able to write it in like these constraints, these like SMT lib style constraints.
So I write an interpreter on this.
Oh yeah, fine. Go ahead. If you can write it as, so this needs to be quantifier free constraints in SMT lib. If you can write it as that, go ahead. You can do that with Cygus. Whatever you like can be a sigma.
I'm sure, I didn't understand all that. So if that's unsatisfiable for all the counter examples you found, doesn't that mean that it's impossible to find such a theme?
Yeah, OHAD is suggesting that you might have written an incorrect sigma and you might want to change sigma and have another go. But yes, if it's unsatisfiable for all counter examples, it's unsatisfiable. Like for the set of counter, for a subset of counter examples, it's unsatisfiable. It's unsatisfiable for all of them. Yes. I forgot what I was going to say. Oh yeah, what goes in the synthesis box? Yeah, I'll go through this, then we'll have a 5-minute break, and then we'll do whatever we have time for in the next one. So, so the synthesis box could have many things in. You could just have a straight up enumerator that goes through all of the programs. It could start from the smallest program, it could start from the biggest program, try to fill them in. Like you could have a probabilistic enumerator, you could stick a neural network in there. But I'm going to tell you about symbolic synthesis encodings because it's another use of SMT solvers. Because enumerating isn't fun, enumerating is just heuristics. It is surprisingly effective, but the symbolic synthesis encoding fits better with my lectures. So, yeah, so what we do with the symbolic synthesis encoding is, first of all, we fix the program size, and we have to add this extra loop on where we're like, oh, increase the program size if you didn't find a program. But okay, so what we do with this synthesis encoding, so let's assume that this is my grammar on the left. So let's assume that my program has a grammar which allows it. So P1 allows my program to be either arg1, arg2, or C0. And then I have a grammar for C0, which allows it to be any one of these bit vector constants. And what I want to know is if there exists like a program within this grammar such that for my counter examples, this is satisfied. And what I can do to do this with an SMT solver is I can introduce some like selector variables. So what I'll do is I'll introduce these two selector variables that select this like P1. So I will say if the first one is true, then P1 takes arg1. I'll say if the first one is false and the second one is true, then P1 is arg2. And if they're both false, then P1 is C0. And then what I will also do is for this constant, I will just create a bit vector. So I can obviously encode and you can have the SMT solver select your bit vector. And I can keep doing that for more and more rows of grammar. But the problem is, as my programs get longer, I start getting more and more selector variables, and I start getting bigger and bigger SMT problems. But this is one way of picking your program without having to enumerate through them. Yes.
If someone who has going to generate semantically distinct programs to cut down the thread space, would that be useful?
If we had a way to generate semantically distinct programs to cut down the search space, would that be useful? Absolutely. The majority of enumeration heuristics are cutting down on semantically equivalent programs. Like if you were to have a grammar that you're just searching through, like if you can cut down on, because all of your grammars are like typically you have a CFG, you have a context-free grammar with like usually they're just like a non-terminal for each type. And so you have they're potentially infinite. If you can cut down on enumerating the equivalent programs, you can like halve this
Okay.
or more.
Please reply.
Yes.
Understand how searches, so you provide a syntax that's all possible programs.
Yeah.
Finite, and then somehow searches through.
So I'm providing a grammar for all of the programs up to a fixed length. And then I'm assigning a set of selector variables, which tell you which one of the production rules to use in the grammar. And then I'm saying, so the SMT solver, please pick the selector variables such that my specification is satisfied for the counterexamples. So the right hand side is your selector variables. So let's say that P1, let's say that my grammar is just, it can only be R1 or R2. What I want to do is let's say that my specification is, I don't know, give me a specification with a program with 2 arguments. I don't know. I want PXY I want it to return X. That's my specification. So I want to say for all X, Y, find PXY, find P such that PXY returns X all the time. And then this is my grammar. And what I'm going to do, I've got a counterexample. My counterexample is, I don't know, when X is 0 and Y equals 1, I was wrong last time. And so my specification here, I'm going to say, does there exist? They've introduced 2 selector variables, let's call it B1 and B2. I actually don't need 2, do I? Let's say that if B1 is true, then we do this, and if B1 is false, then we do this. So I only need 1 selector variable. And I'm going to say, does there exist a B1 such that this spec is true? And I'm going to, in the place of P, X, Y, I'm going to write this program, which becomes, how am I doing this? If B1 is true, then return R1, otherwise return R2. And I'm going to say, does there exist a B1 such that, and then I need to put X and Y in here as well. So okay, so this has now become X and this has become Y. Does there exist B1 such that when X equals 0 and Y equals 1, this if statement returns X. And you're now, the only free variable in here now is B1. And I need you to, I'm going to ask my SMT solver to find a B1 such that this statement, which is my program, satisfies the spec for my single counterexample here.
Can you have an arbitrary program kind of disobedience? Let's say all is Y, PXY equals G of X, where G is an arbitrary program somewhere else.
It can have arbitrary programs that you can, as long as they're defined. If you have another function, if you want to say that P could potentially make a call to another program.
Actually, here PXY equals, let's say f of X equals Y.
You can do that as long as f of X is true. As long as f is defined.
And f is just some program that I wrote just together with my SMT program.
As long as you've given me the definition for it, yes. But you can't have any uninterpreted programs in here because then it becomes a universally quantified uninterpreted function. But as long as you've given me the definition for any functions, you can use functions wherever you like in here. Yeah. Okay. What was coming up next? I forget what was coming up next. Okay, this is the end of me telling you what goes in the CGIS boxes. I suggest we take 5 minutes unless there are currently questions. Okay, 5 minutes, which means we start again at 10. 2 minutes to 10. These for S3 buckets, don't let everyone in. So I'm going to talk about Euclid 5 first. This is basically just me telling you that there is another tool in your arsenal for generating SMT queries and also for generating Cygus queries. It is on GitHub. We have a tool paper at CAV this year. I'm now going to show you what it looks like. If you have a go with this and you find any bugs in it, please file GitHub issues because I'm the person that has to respond to them. And if you don't file the issues, I never find out about them. I don't promise to respond promptly in any way, but I will try. So we are writing transition systems with Euclid 5 to be like, which is useful for many things. Like we had a transition system before when we had these initial conditions and the transition relation. So if you want to code up anything that has loops in, transition system is pretty useful. And so our Euclid models start with a module. So we have a main module. Think of this as being like your main function. We have a system description. This allows you to declare variables and it allows you to give initial states, and it allows you to give a transition relation. Same thing where apostrophes mean, like the prime notation means these are my next state variables. We support basically any type that SMTlib supports. And we support some types on top of that we can then turn down into SMTlib. So things like enums we support as well. But essentially, if it's in SMTlib, we will support it. You then write a specification in the form of an invariant or a property. These are synonymous. And you then write a proof script that says how you want to check it, and then says, check it for me, please. So there are other ways of checking things. You can do bounded model checking, you can do K induction, and you can also do things like say, okay, now please print me the counterexamples, now check this property instead. By default, it checks out all the properties in the file. So if you do induction, it will check that the property holds at the initial state. It will check that it holds on entry to either, if it holds on entry to next, it will hold on exit. This one doesn't actually hold. Also, has anyone noticed what this file is doing? It is doing Fibonacci. Okay, why doesn't this hold? Actually run it. Actually, let's run this and see. It might be negatives again. I don't think all the problems go away if you have. Yeah, I mean, lots of problems would go away if we didn't bother using bit vectors, right? Like how many security vulnerabilities and bugs depend on bit vectors? But unfortunately, we do still need a way to store numbers in computers. Do you think all of our problems would go away if we took away computers? So that passed, so let's look at the models I have and check which one we're running. That's bounded model checking. Okay, so that passed with bounded model checking. I think, which one has induction? Handy, the one with induction at the end. Okay, this is the model we had up before. These are real, oh, that file didn't exist.
Exactly.
These are mathematical integers and not machine integers.
Can you write the 32? You want to model it?
If you want to model int32, then yes, you can write that as a bit vector.
Did you put the objectives?
Did I put the,
If AI equals AJ, then I equals 2. If of 1 is equal to if of 2, if 1 is equal to
I didn't put that in, but that's inherent in the definition of the, like we're in linear integer arithmetic. We're not in a, we don't need to define all of the concepts of linear integer arithmetic. And I think yeah. So that failed, and it also didn't print me a counterexample, which is not very helpful. Let's print a counterexample. Who knows if I can remember the syntax for showing counterexamples? I'm not sure I can remember it off the top of my head.
I'm sure it's hard to find out.
Oh, I could show you how to find out. Fine. See, now we know it's v.print CEX. There's documentation as well, I promise. Does everyone not use git grep as their way of remembering what they've written? Counterexample. Okay, so the counterexample it's given us, it says we have failed the step case, and it says we failed the step case when A was -1 when we entered the next block, and that gives us B as -1 when we leave the next block. So OHAD was right, negatives were the problem. What's it doing underneath? It's building the query above. So if 1 is P1 and 2 is P2, it's building this SMT query that is asking whether P1 is violated or P2 is violated, and it's giving it to an SMT solver. Fairly straightforward. If it's doing bounded model checking, it's doing this, but it's doing this with a property for each step so that it can tell you whether which step it fails on. Fine. We're too dumb to figure out how to strengthen this by ourselves. So what we want to do is we want to synthesize this strengthening. So what we're doing here is we're putting in this synthesis function, which is called H. And we're going to put this into our invariant, and we're going to say find H such that we pass all our verification conditions. That's the solution. And when we run it, it's going to generate this Cygus formula. So it's going to generate this formula that says that there exists an H such that for all of the inputs, our properties are both satisfied, are both true, and is going to give it to a Cygus solver. Let me see if I've remembered which one of this. Yes, question.
So would you think of the synthesis line as part of the system description, or is that more like an input to the There you have this section.
Okay, so synthesis function, I would think of that as being part of the system description. So if you were defining, you could also have an uninterpreted function in Euclid, in which case that's the same as defining a variable that is like n-ary rather than null-ary. So yeah, I would count functions as being part of the system description. Yes. And this will then synthesize the answer to the whole, which is a greater than equal to 0. Fine. Yeah, so how is it working underneath? So we've got this symbolic simulator underneath, which is generating these properties. And then it's spitting this out to an SMT solver, or it's spitting it out to a Cygus solver. This is fairly unsurprising, I think. Yeah. I think I might have time to talk about Zelkova. Yeah. Which no one cares about. I wish I hadn't asked that now. So upsetting. Does anyone use S3? Okay, a few people use S3. Have you noticed this little thing at the top that says like public or not public? Like, no? Oh, that's really upsetting. This is why this stuff is necessary. People don't realize when they're making their buckets public to the world, and people don't care even when they should. So this is running SMT solvers. This is running millions of SMT calls daily. This is like, I don't know if it's the biggest industrial use of SMT calls, but it's pretty cool. Okay, so a bucket is where you can, so this is Amazon's public data storage. If you want to dump a bunch of data on the internet somewhere, you can put it in an Amazon S3 bucket, and you can then define who has access to it and who can read from it and who can write to it. And you define that with access policies. Access policies are surprisingly hard for users to write. To be honest, I find that, so it's based on their IAM system. I find the whole Amazon like policy system like very hard to use, but I don't think I'm alone. So a few years ago, there were quite a lot of news stories about public buckets being a real security issue. I recommend going to read this article, but I'm going to give you some of my favorite ones. Okay, so a private company working for the US exposed a whole bunch of battlefield imagery. So they're working for US defense. They just put this in a public bucket. So that was fun. US voter records. Again, this appears to have been like just for one state, and there seems to be a private company that was doing it. Yeah, they just made 200 million American voters' personal data available. Just put it in a bucket, nice public one. Dow Jones & Co. released a whole bunch of personal information. And my favorite, WWE. Like, if there's any of my personal information that I don't want released, it's the fact that I am a fan of WWE wrestling. And they released 3 million wrestling fans' data. And you can actually search for how many like public buckets there are. Like, people have now made websites where you can be like, oh, here, like it'll search all the buckets. It'll find how many are public. Like, it's not hard to find. If you're going to stick your personal data on the internet for everyone, like, this is a pretty good way of making it public. These are what your policies look like. So your effects can be like allow or deny. And this is saying that this principle here is not allowed. In theory, that's what we intended to write. What we've actually done is we've said everyone except this principle is allowed. So we intended just to rule out Joe here, and actually we've said, okay, fine, Joe's not allowed, but literally everyone else in the world is, including all of my pigeons with opinions from yesterday. And yeah, so what do we do so basically Amazon are checking the permissiveness of your policies, and they're doing this by comparing two policies. So they're taking P1 and P2, and they're saying, okay, if P1 implies P2, then that means that policy 2 is at least as permissive as policy 1. So like everything you can do in P1 is allowed in P2. So anyone who can access P1 can also access P2. So it's just a permissiveness comparison. So what they'll do is they'll say, okay, I've got a policy that allows unauthenticated access to everyone, or like allows unauthenticated users, and they will compare your policy to that, and they'll use that to check whether your policy is possibly doing something you didn't intend. So they do that by turning this policy into a formula. And so they're using strings, basically. They're using a string solver. I think they're also using integers. And then they're able to deploy this to SMT solvers. They're having to do some quite neat stuff with regex as well, but yes. Oh, the fixed example, just in case you're using S3 and have realized that your buckets are public to everyone, you needed to write deny. But we can, yeah, so if we look at this example from, so they've got a paper on the gubbins behind Zelkova. If we look at this example, we can write policy, like we might want to write a policy that says, so I don't know, in a world where we're allowed to put exams in S3 buckets, which we're not, probably for good reasons, we might have an S3 bucket where like, okay, the students can read the exam, the TAs can read both the exam and its answers, and that seems kind of reasonable. And if we'd written policy X, that seems sort of right. Or we might want to write policy Y, so that everyone can access all of the contents of like this, of my CS240 folder, but the students can't access the answers. That might be what we want, but it's hard to tell which one of these is more permissive than the other when we just look at them on face value.
What we verifying? Is it that really just want to check to see if they've set permissions as it's more validation process?
So the property that they're verifying is, can unauthenticated users access your bucket? And they just want to give you a warning that says if unauthenticated users can access your bucket, then you'll get a flag that says your bucket is public.
Who sets the users?
You write the, so, okay, so by unauthenticated just means not even log, they don't even need to be, like if any Amazon account, anyone with an AWS account can access your bucket, then it's public. Or even anyone without an AWS. So I think your deny supersedes your, like, I think that overrides the allow in that I think Y still says that students can't access answers.pdf, which is fine. That's not actually the issue with Y, but you'd have to check with, I don't know what the order of precedence is of allow and deny. But yeah, because it's quite hard to tell which ones of these are more or less permissive than the others. So what we do is we turn these into formula again. And so if we've got two allow statements, that's like a disjunction. If we've allowed the students and the TAs, so that's allow students and TAs, clearly like we want the or of those. We don't need to be a student and a TA to get access. And if we've got a deny statement, this answers it, it's a conjunction. So if you've got a deny statement, that's conjoined with your allow statement. Fine. I should have hidden the answers. I should have made you guess. I should have made you guess which one's more permissive. Okay, all requests that are allowed by X are allowed by Y, and we determine this using an SMT solver by checking X implies Y. What if I flip it the other way around? Are these two policies the same? You don't know what I've stored it, yeah? No?
That would be the case, because you allow everything you allow public, right?
Yeah. Yes, they are. Yeah, so Y allows everybody to access, it allows everybody to access stuff in CS240, and the only thing it restricts is students getting the answers, so it makes the contents of CS240 public. Yeah, I just thought it was quite a neat use of SMT solvers. Yeah, anyone can access the files in CS240. Yeah, so they have their own sort of regex extension of Z3, but essentially almost all of this can be done with commercial SMT solvers, and they deploy a whole bunch of, they deploy sort of 3 of them in parallel, and then just take whichever returns the answer first. Yeah, so actually I might even be finished early. So by the end of these lectures, I told you that you would know what SAT is, how to encode problems into SAT and SMT, which solvers are available and how to use them, some tools to generate their queries, and some instances of how they're deployed in the wild. And I told you that you wouldn't know how the details of how they work, but you'd have a high level of them. Is there anything in here that you feel like you should know that you don't?
Maybe you can explain in 8 minutes how it works.
8 minutes. I can tell you, I can give you a summary of the stuff I didn't tell you so that you know what you can go and search for. I did not tell you, so I told you at a very high level how SAT solvers work. I did not tell you about any of the heuristics for how you assign the variables and how you pick which branch to go down when you're doing this backtracking. I did not tell you how far you need to backtrack and how you determine how far you need to backtrack. I did not tell you how to do incremental SAT solving either. So incremental SAT solving is where if you've got similar problems, you might want to pause the solver at a certain point and then be able to backtrack to a certain point. So you want to be able to pop off clauses effectively, like the SMT solver. So you want to be able to solve something, reverse a little bit of it, and then continue solving the next similar problem. And I didn't tell you how that works at all. What didn't I tell you about SMT? I did not tell you how the theory solvers work for different SMT solvers. I alluded to the fact that linear integer arithmetic might be simplex, but I didn't really tell you that. I did not tell you how bit vector theory solving works, although I alluded to the fact that you might be able to do it with bit blasting, where you turn it into a SAT formula and create a Boolean for every bit. I did not tell you how you combine theories. Didn't talk about Nelson-Oppen, which is how you deal with multiple theories in an SMT solver. I didn't tell you, which is actually useful information and not an in-depth bit of information, I didn't tell you that if you have a problem that involves combining theories and you can avoid combining theories, please avoid it. The number of times I've had sort of students produce formula that are a mixture of integer and bit vectors, and they've done it because it felt like the integers made sense as, I don't know, a counter variable or something. But the combining the two has made the whole problem harder than just using bit vectors all the way through. I didn't tell you how to solve quantifiers at all. That's an entire other course. We didn't talk about like first order quantifiers. We're not going to. We're definitely not going to do that in the remaining 4 minutes. Yeah.
One thing is finding is checking. What I'm looking for is a theory. So I just want to constrain sort of a guided theory discovery. Right, so let me try this theory here, and then set sort of please explain to me what are the constraints that make my theory wrong.
The constraints that make your theory wrong. But then if your theory is wrong, then the definition, like it's the definition of your theory symbols that's wrong.
The jeopardy is that's all. It's kind of like, so I'm looking for, I want this problem to be solved. Please give me a theory.
But I can always come up with a theory where the problem is solved, right? Because I can just define my own. I can just define my own theory where, like, yeah, I mean, I can redefine equality if you're going to let me define my own theory. So
I give you a partial theory.
So what you're saying is you want me to give you the definition of the symbols such that your thing passes?
Yes.
So could I not make those symbols uninterpreted functions? And then you want me to find the definition of the uninterpreted function such that your thing passes? I think you could do that. It's going to be quite messy. I think you could do that with uninterpreted functions. I also didn't talk to you about some work that I've been doing recently where we combine oracles with satisfiability and with synthesis. And this allows you to put in, like, it allows you to define an interface to an executable and then integrate that with the SMT formula. So then you can say, you can say, if you call this executable, it will generate this constraint for you. So you can pull back in constraints that way rather than needing to define them all in these sort of Lispy sort of SMT language, which might be useful if you wanted like to build an interpreter, for instance, because I can't recommend building interpreters in SMT lib. Yeah.
What's really hard for you? So if you had something of a solution to something.
Hard for me or hard for SMT and synthesis?
For the community. This problem, what's really, really hard?
So higher order, like synthesis. So this higher order, this second order logic problems, higher order SMT is really hard. It is essentially solved by heuristics. Like all of this enumeration, like all of the Segas algorithms are heuristic driven in some way. And getting synthesis to be scalable to the point where it's useful is really difficult because it's so heuristic driven. Like we need some way of taking the kind of scalability that you can get from what I'm going to call casual synthesis, like the informal synthesis, and lifting it into formal synthesis. I would say what is hard for the verification community is building, like getting the tools to work in a way that people in industry want to use them. Like you're not going to get people sitting down and building their SMT formulas by hand. You might just about get them to run CVMC, but you're not going to get the majority of them to run CVMC. Like we don't have fully automated, like plug and play verification tools, really. And when we do, there are things like Coverity, which is a static analyzer based on pattern matching, essentially. And it gives you so many errors, like so many bug reports that it's not meaningful. You're not going to look at all of them. So then you may as well not know about them. Yeah. What are the applications? Currently, I wouldn't say that synthesis is, I don't think synthesis has people in industry using it right now, other than some niche people trying to use it to synthesize loop invariants. One of the main applications is probably loop invariants. One of the things I would like to use it for is coming up with these like extra verification artifacts. So you need to, like, strengthening invariance is just one example of when you might need to place assumptions on your verification problem to make it pass. So some of your assumptions might be assume that this function follows this new theory I've come up with. In my like dream world, I would like synthesis to be good enough that you could you could have like regular programmers using it. Like instead of Copilot, they would have like Copilot but in a Segas loop, and they'd write like a little spec. Maybe they'd write it in natural language and it would get translated into something formal, but maybe I'm just dreaming. Oh yeah, Flashfill is Segas. That is the best example of formal synthesis in the wild. What do you use it for? Oh, what is it? Flashfill? Oh, in Excel, if you fill in a couple of columns of data and like the answer, Flashfill will tell you, it will infer, so you've got a few columns and you've got the results. Once you do that for a few, it will infer what the transformation is in terms of like Excel functions, and then it'll just fill in, it will suggest the rest for you. It's really clever. It's really neat. It's essentially doing Segas, but its specification is the examples that you've given it so far, and it's doing it on string transformations with like the grammar of Excel string manipulation functions. There is work in academia using synthesis to try and explain machine learning. So trying to come up with expressions where you think that expression summarizes some neural network that is doing something and you want to know what it's doing. Yes. Someone asked what it's used for in academia. I have seen it used for many things. I've seen it used, so I've done some work where it's used in control synthesis. I've seen it used at a small level for doing sort of like replacing libraries with modern libraries in code. I've seen it for sort of data wrangling. Autonomous driving, I've seen, I guess that falls under control synthesis. Struggling to come up with more applications. There's a small list. I guess if you took a look at PLDI and CAV at the past papers, that would give you an idea of where it's used.
The programming samples here are all imperative.
Yes.
So, but let's say when, so, and that makes the constraints very logic.
Yes.
And you are always reasoning about the consequence for the sort of, that's why that's where the constraint that comes out of this SMT solver is the consequence rule. That's where the output is.
Yes.
So let's say that instead I have a functional program. So my constraint system looks more like a type and effect system. I have a, like, so my sigma is a type system that's annotated with some, where I annotate either the type of each term or the expressions, sub-expressions themselves with constraints. And I want to find those. It seems like it was built into this language that here is a C-like imperative language that has the built-in keyword invariant, and you have to specify your invariant in a very logic-ish way, right? But what if I really want to specify how to say invariant, or where the output of the invariant comes from?
Okay, so the question is, this is all very imperative, and we're using a lot of sort of imperative styles like core logic. And what if it was,
Yes,
what if we wanted?
Really fit into a lot of academic work if it's functional.
It doesn't fit into a lot of academic work, because academic work is functional programming. I think that's slightly unfair to academic work that uses imperative programming. But I'm going to make a claim here that, so I don't know the answer. I don't know why this isn't done for functional. I think this, okay, so I think this stuff could be translated over to functional programming. That work might exist, I don't know. I'm going to hypothesize that most of this stuff is done for C-like languages because the software verification competition is on C, and because C-like languages are more widely used, or like, so this originated with hardware verification and then moved to software verification. So you've got this community where they're used to C. And then when you want to deploy this stuff in the wild, you've got, so CDMC does C and C++ and now Java. So they've sort of picked the big languages that they think they're going to have impact in industry with. So whilst I think I don't see a fundamental reason you couldn't have this sort of stuff for functional programming, it might exist. I think we're driven by industry.
But the off-the-shelf tool doesn't give you.
Well, SMT lib isn't imperative. It's list.
Yeah, okay.
But you can, yeah, the interface, like the tools I have shown you are imperative because I like C++. Yeah.
So, kind of related question. The one we use in functional programming is for you have a type system and you generate all the constraints between the types, and you want to solve whether there is a type assignment.
Yeah.
One of the things that would stop me from using it in the compiler that I use, as I understand, is that unsat doesn't give you any information. Like it spits out unsat.
Okay,
but
so
I want to tell my user why I can't find the type of something. And if I just say it's not possible, well, they've got no information on that.
okay, so I didn't tell you, one of the things in the list of things I didn't tell you about unsat cores and how to get an unsat core. There are methods for coming up with like the unsat core of your formula, which you could then reverse back and you could try and come up with something meaningful to the user. I don't know if an unsat core would be meaningful to the user in its raw form because it would just be a set of constraints and you'd need to reverse it back to tell them where it came from. But you can do that, and many solvers will give you an unsat core if you ask, but it's extra work, so they don't tend to. Does that help? Cool. I think that's, well, we're now into the break. I used more than my 8 minutes. I'm done.
All right.
Yes, so let's break for coffee and we'll restart with James' lecture at 11. Is that correct? Yes, that's correct. Yes, 11. And let me remind you once again that if you haven't paid for your recommendation yet, this is a good time to go to the front desk